Hello everyone. I hope you all are having a good DevLive event so far. Today I'll be talking about how you could integrate your Kubernetes-based application or Kubernetes-based microservices into various different networking patterns. Before we get started, a quick introduction about myself. My name is Ajay Chhabria, and I'm a product manager at Oracle Cloud Infrastructure, focusing on building a managed Kubernetes offering called as Oracle Kubernetes Engine, which is being used by a lot of developers to move their microservices onto public cloud. So here's what the agenda would look like. I'll start off with a bit of a networking foundations recap. So summary of base building block of OCI networking. If you're already familiar with the OCI networking, it's going to be much easier for you to translate them into the Kubernetes world. If you're not familiar with the OCI networking, it's going to be a quick recap to get you on road with everybody else. Then we'll try to understand how you can configure networking into OKE to send your traffic from south to north, from pod to internet, or from pod to the OCI services, or how you can route your traffic from pod to pod or microservices to microservices going east to west. And then we'll switch on to the advanced topics like exposing services using different types of load balancers that we have in Oracle, network policies using Calico, network security on the VCN side, service discovery using DNS, and lastly, service mesh. So this is how a typical managed Kubernetes cluster architecture looks like, right? So there are two components in the Kubernetes world. One is the control plane, what we call it as the heart of the Kubernetes. And then on the right, in the customer tenancy, you have something called as your workload, or a data plane, or a set of compute instances, right, on which you deploy your microservices. So in today's talk, I'll be focusing on the networking that happens mainly on the right in the customer's tenancy, wherein you basically, as a developer, have an API endpoint, which is nothing but a cross-tenancy VNIC attachment, and then how you configure the networking for your pods, your microservices on the compute. And then how you expose your application or your microservices to the outside world wherein your users would be using that. So this is how we'll be focusing the networking mainly on the right side. So this is what a typical Kubernetes topology looks like in a single AD region. A region is nothing but a geographically localized region, right? And AD here stands for availability domain. So think of an availability domain as nothing but a data center, right? And within an AD or within a data center, you would have multiple FDs. What I mean by FDs here is fault domains. And fault domain is nothing but a grouping of hardware or a grouping of an infrastructure where all the networking really happens, all the cabling really happens, right? And when you as a developer think about networking, there are a few questions that you need to really ask yourself. What kind of internet access would really require for your pods, for your worker nodes, for your API endpoints, for your load balancers? And then you start thinking about how you would size your worker node and spread it across the fault domains, right? And then you would have different type of gateways that would really define your connectivity to the internet or to the OCI service, right? And lastly, but not least, it could be load balancers, how you would be accessing your applications and probably get into your worker nodes via something called as a bastion host or the admin host. And then when you switch on from a single AD region to a multi-AD region, things would not really be different. It's probably the same. In a multi-AD region, you would have multiple availability domains, right? And within each availability domain, you would still have those many number of fault domains. So you as a developer get a choice to pick and choose how you want to spread your worker nodes, how you want to spread your applications, how you want to spread your pods, your microservices across different availability domains, different fault domains, etc. And then the JavaScript that I've written on the right is nothing but just trying to show off my Java skills to simply just it would print up a line that worker nodes would be equally distributed when you are in a multi-AD region. Now, the first component when we think about networking is something called as VCN, or what we call it as Virtual Cloud Network in OCI, right? VCN is nothing but think of it as a logical network. Think of it as your virtual private data center on which you can control whatever you want. You can configure networking, you can configure your own IP address CIDR block. So in this example, there's a multi-AD region called as US Ashburn 1, right? The first thing you as a developer, what you would do is you would define something called as a CIDR block. So in this example, I've taken 10.0.0.0/16, right? And once the CIDR block is defined, you would start subdividing them into smaller networks called as subnets. Now, in OCI, we support two different types of subnet. One is called as the AD-specific subnet, which we call it as availability domain-specific subnet. What I mean by that is, let's say if I have a subnet B, C, and D, which are my AD-specific subnets, meaning I cannot create a worker node 1, and select AD2 if I want to deploy things in AD1. I have to go with AD1. If I have to go with subnet B, I have to really go in that AD1 specific domain. So here in this example, I've created 3 AD specific subnets called as subnet B, subnet C, and subnet D. But then on the other hand, there is a choice of having a regional subnet wherein you can have a subnet that would have its presence across the ADs, and you as a developer, you are independent to just deploy your Kubernetes resources in wherever ADs you want, right? So in this example, I've created subnet A as a regional subnet, but I've chosen, I'm not really bound to create any of the Kubernetes resources in any of the specific ADs. I've spread API endpoint, my load balancers, and my pods across in a single subnet. Now, that was about the VCN, how we get started. Now, let's try to understand how you as a developer can control the traffic coming from the internet or from any of the OCI services that you would use for your microservices. So in this example, if you could see the load balancer on the very top center, it has a public IP address, right? And then it is using something called as a managed gateway that we offer in OCI called as the internet gateway, right? So in order to send the traffic from the load balancer to the internet, any traffic goes via the internet gateway. So not only the load balancer can send the traffic to the internet, but also the traffic from the internet can come and reach out to the load balancer. So what you need to really do is you need to provide a public IP address to your load balancer, and you also need to provide your configure a routing table inside that VCN that would really define that any traffic here, in this example, for example, going to 137.254.7.178 needs to go via the internet gateway. Now, let's say you as a developer have a requirement that I don't really want my worker nodes to have a public IP address, right? But I still want to do some YUM update from my worker nodes. I want the traffic to just go one way. I don't want the internet to access my worker node. That is when you would use something called as the NAT gateway, which is another type of gateway that we support in OCI that you could use it in OKE, and send the traffic in a one-way direction. So the traffic would go from the worker node to the internet, but none of the internet will be able to access the worker node, because the worker node does not have a public IP address at all. And one thing to add here is that in the internet gateways and NAT gateways case, your traffic is having a footprint over the internet. But let's say you have a requirement that you don't really want to have any footprints over the internet. You want to access a specific OCI service, for example, autonomous database, for example, from your Kubernetes cluster, right? And you don't really want to have a footprint over the internet. That is when you could use a third type of gateway, what we call it as service gateway, right? That would route the traffic from the Oracle backbone network. You don't really need a public IP address. The traffic is not going over the internet, and you could still access an OCI or an Oracle service. So this is how you would control the traffic going south to north and north to south. Now let's try to understand how a typical Kubernetes networking model really works, right? So In the Kubernetes world, you may have n number of microservices, right? And your microservices are nothing but it's translating them into pods. So by default, every pod would have an IP address, right? And every pod will be able to talk to another pod until and unless there is a network policy plugin that is applied between the pods that would control the communication. And the actual networking implementation happens through something called as the container network interface. That is nothing but it's a plugin that implements the networking model. So unless and until you don't have that CNI, the networking won't really happen between pods. So CNI is a must to have that communication between them. So similarly, in OCI, we have a VCN CNI that is used for any networking between pods. So any traffic going east to west can choose to use, you as a developer can choose to use OCI VCN CNI as one of the networking implementation to route your traffic from east to west. So what this really gives us is the first thing first, these pods get an IP address from the VCN CIDR range that I showed earlier. And since they're getting an IP address from the VCN CIDR range, these IP addresses are accessible either from the on-premises or from other VCNs that appeared to the VCN where your Kubernetes cluster is sitting. And then there is no special type of additional overlay networking like other CNIs like Flannel would do that for you. You'll be able to take all the benefits of the VCN, including flow logs. And then you would also be able to apply all sorts of security lists and policies from the VCN for your particular pods. Now let's try to understand how the traffic would flow when you're using the OCI VCN CNI. So let's say you as a developer created an OKE cluster and you configured OCI VCN CNI as your networking component, right? So your worker nodes, in this example, there are 2 worker nodes, the gray boxes you see, would have a minimum of 2 interfaces. So the first interface, which you see it as ENS3, right, is nothing but the main VNIC that you would use for management purposes. But there is a secondary VNIC also attached to the worker node, which would have a bunch of secondary IP addresses associated with it. These secondary IP addresses are nothing but the IP addresses that are pre-allocated to the worker nodes, and they are dedicated for pods. So as pods keeps on coming and going, right, they get this IP addresses from the secondary IP address range that you see it right here. And let's say in this example, there is .248, .249, .250. They all are getting the IP addresses from the secondary IP address range. So let's say if 248 wants to talk to 249. So when the traffic instantiates from 248, right, native pod CNI knows that the destination 249 is sitting in the same worker node. And that is when it won't really send the traffic all the way towards the secondary VNIC. It will make sure that the traffic is there local to the worker node, and using the IP VLAN trafficking, it would just simply send to the traffic to the 249. Versus if let's say 248 wants to talk to 251 sitting on a different worker node, of course the worker node would know that .251 is not local to the same worker node, and it would simply, the native pod CNI would simply send the traffic out to the ENS5 interface, the secondary interface, which would send the traffic all the way to the VCN, and then VCN would handle the routing because it knows that .251 is a part of VCN, and it knows that it is sitting on the second worker nodes, and it has a secondary IP address for that particular worker node. So VCN would route the traffic to that particular specific worker node, and then eventually the native pod CNI knows how to redirect the traffic to the pod. So this is how the traffic would move from one worker node to another using what we call it as the OCI VCN CNI. Versus when I compare it with Flannel, which is also another CNI that we support in OCI, and it is a standard CNI that is being widely used across the Kubernetes world. In this case, there is an overlay, there's an additional overlay that is getting created. So if you see in this example, there is a yellow box called as the pod network which is nothing but an overlay network that is being created. So 10.244.0.0/16 is an extra additional overlay network that gets created. So VCN is not really aware of this overlay network. VCN would not really know what's going to happen through the traffic. So when the traffic wants to go from 0.4, which is the pod on the left worker node, to the pod on the right worker node, there is an encapsulation that really happens by VXLAN in the packet, right? And that encapsulation happens by something called as the Flannel daemon, which runs in that specific worker node. So the packet gets encapsulated just before coming out of the VNIC, and then gets decapsulated just exiting out of that secondary VNIC of the second worker node. And then eventually goes to the Flannel daemon, and the Flannel daemon would again decapsulate the packet and send it to the right pod. So as you all know, that Flannel CNI is a very easy and simple to use CNI, but it would really require some sort of overlay networking, something to really think about, versus the OCI VCN CNI, which would not do any sort of overlay. Now let's try to switch our gears onto the advanced topic called as exposing services, right? So today, whenever you're writing your microservices, right, you want to expose your service to the outside world. And Kubernetes supports 3 types of ways that you expose your service. Like one is the cluster IP, which is an IP address that is only reachable from within the worker node or within the cluster. And then the second type of IP address is something called as the node port, wherein you would use the IP address of the node and port to access a particular microservice. But then there is a third type of service that you would expose is called as the load balancer, right? So in OCI, we have natively integrated our load balancer with using the OCI load balancer, which is a layer 4 to layer 7 type of load balancer. So if you want to expose your microservice and use our OCI load balancer, this is the annotation that you would just have in your service definition file. And it would create a load balancer for you. It would create an OCI load balancer for you. You would add extra annotations to it to define it as either public or private, or different types of SSL termination or SSL tunneling. And based on what you configured, you could have that features in your OCI load balancer. Versus if you choose not to use a layer 4 to layer 7 load balancer, but you want to use a layer 3 or a layer 4 load balancer, that is when if you have latency sensitive applications like IoT or databases, wherein you want to not have that proxy load balancer, you want to have a pass-through load balancer, that is when you could go with OCI network load balancer, which gives you layer 3 to layer 4 capabilities, and it would also load balance the traffic for you. And don't want to forget to mention that it's a free OCI resource. We don't really charge you for using an OCI network load balancer. This is something that you could use for free. Now, when you use a network load balancer, right, there are 2 options that you get. The first option is whether you want to preserve the IP address of the client that is coming from the internet. So there could be situations, there are times when developers want to see from where exactly the client IP address is coming from where exactly the traffic is coming from. And that is where the developers want to preserve the IP address in the packet itself. So there is a mode called as local mode, wherein if you turn that mode on, right, and this is the specification that you define in the service definition file, it would preserve the IP address of the traffic all the way from the internet, all the way till the application. So as you can see in this example, 1.2.3.4 is being preserved all the way till the pods. You could add something like a virtual firewall sitting behind your network load balancer that is inspecting the traffic. There could be a use case where you want to inspect the traffic, like which traffic is coming from the internet, and take actions accordingly. So this is one of the use cases. But one thing to remember in this mode, right, if you don't configure things, the traffic would not be load balancing properly. So in this example, as you can see, the pod on the second worker node might receive 2 times the traffic compared to the pod on the left worker node. And the way it works is, let's say the first traffic comes from the client, hits the network load balancer. The network load balancer sends the traffic to the first worker node on the left. the worker node sends the traffic to 10.244.0.1, right? The first traffic went to 0.1. Now the second traffic would go all the way to the NLB and go to the second worker node and reach the traffic to 1.1. Now the third one would go to the second worker node, but to the second pod, .0.2. And the fourth would again go to this right worker node and hit 1.1. So as you can see, 1.1 is receiving 2 times the traffic compared to what other pods are receiving. So if you're not really planning things well, this is where your traffic might not be distributed properly. Compared to the cluster mode, wherein your requirement that is, you don't want to really preserve your client IP. You want your traffic to be equally balanced across the worker node. That is when you could go for something called the cluster mode, wherein in this mode, the worker node would not really care if there is a pod local to my worker node. If there's no pod, like you can see on that diagram, it's going to forward that traffic to the worker node, which would have that respective pods. So this is where it happens in this particular cluster mode, where traffic is load balanced equally. You don't have to really care about having individual pods explicitly. And our network load balancer also supports UDP as a protocol. So if you're having, let's say an application or a game server application wherein you strictly want your application to support UDP as a protocol, you would still use network load balancer, which supports UDP. And this is how you would just define your specifications. You no longer require a fleet of UDP servers. You can just have one load balancer, which would take care of your UDP-based workloads as well. Now, in OCI, we support something called as bring your own Ingress controller, wherein you can use any type of Ingress controllers like Nginx or Traffic to load balance your services, right? So if you have like n number of microservices, you could have one Ingress controller or one Ingress definition that would create an OCI load balancer for you. So we have natively integrated Nginx, for example, with our OCI load balancer. So let's say if you have an Nginx Ingress controller, it would have the deployment in a format of a pod. So as you can see, there is an Ingress controller pod being distributed in every worker node, which is nothing but the Nginx Ingress controller deployment. Now the pods that you see, right, is nothing but your actual service. It is your actual application. And then what you would do is you would expose your Nginx deployment, not your deployment, but your Nginx deployment, which would create just one OCI load balancer for you, right? And then it would be the load balancer would be one that would be doing the routing for you. And as you keep defining Ingress objects, right? As you keep defining Ingress objects, the control plane would really know. The Kubernetes master would have all those definitions. And that Nginx deployment pod would keep pulling all the entries of the objects and start understanding how should I route the traffic accordingly to which application. So as you define, like, in this example, I'm using Hello World as an example, right, which is doing nothing but a path-based routing. So for any Hello World application, the Nginx Ingress controller pods would know, how to really route the traffic accordingly, because it has pulled the definition objects from the Kubernetes master. So this is how you would use your bring your own Ingress controller in OCI. And then, like I mentioned earlier, right, every pod will be able to talk to each other until and unless you apply a network policy plugin that would control the communication between pods. So network policies are nothing but think of it as a virtual firewall that would be deployed in a flat network, right? You don't have to really have a proper firewall as pods keeps on coming and going. Pods are like ephemeral, they come and go, right? So you cannot really control the traffic based on IP addresses and ports using network security groups or security list in the VCN, right? You would use something called as a network policy that would really define what type of traffic would be controlled between namespaces or pods or IP addresses, CIDRs, be it whatever. And Calico is one such network policy plugin that you could use with OKE to define that network policies between pods. And then network security groups, right? There are other Kubernetes components like API endpoints, worker nodes, load balancers, right? So you could restrict you could define what type of traffic would be allowed, or to be communicated between the API endpoints or between worker nodes, using network security groups, right? If I compare it with security list in the VCN, security list is tied up with every subnet, right? So if you're planning to use security list, you have to make sure that there is the Kubernetes components like API endpoint, worker nodes, and load balancers are sitting in three various different subnets. Unlike in this example, as you can see, I'm just using one subnet, one big subnet for multiple clusters, right? And there are two clusters here, OKE cluster 1 on the top, OKE cluster 2 on the top, at the bottom. And then I have just 3 NSGs profiles that I've been applying to every Kubernetes component. And this policy or security list really applies at the VNIC level. So you don't have to really create a security list for the entire subnet. You could just have one subnet, ignore the security list, but have NSGs applied to different OKE components. And then we also support something called as the private API endpoint. So let's say if you are planning to use a private OKE cluster and you're worried about still having a public IP address for your API endpoint, you could go for something called as the private API endpoint, which would allow you to have an endpoint sitting inside your VCN. You don't have to really worry about thinking about where is my API server, where is my API endpoint, is it having a public IP address? No, that's gone. You could have one single API endpoint which would act like an OCI VCN resources, onto which you also apply features like NSGs, and you could make sure that it's being controlled, the traffic is being controlled to whoever you want to give an access to. So when we think about service discovery, right, the first thing that comes into our mind is DNS resolution, right? Since DNS is something that has been used in service discovery for years, right? So whenever you create a microservices, right? So let's say in this example, I have a microservices called as Kubernetes. The way it gets registered into something called as CoreDNS. So CoreDNS is something that registers every service that you define. So the way it does is, it registers the service name, and then it concatenates with the namespace name. So in this example, as you can see, Kubernetes is the service name. I'm doing an NS lookup, right, using a DNS utils pod, and service name dot namespace name, and then it concatenates with something called as service.cluster.local. And that is how the CoreDNS registers the name of the service into itself. So let's say if a pod or a service wants to do a service discovery of another service, right? So the first request would go to the CoreDNS. Now if the CoreDNS is unable to do a resolution, right, that request gets forwarded to the VCN resolver. And then if the VCN resolver is not able to do a discovery, it would eventually go to any of the upstream DNS servers that you may have configured. So this is how usually the flow of that service discovery really happens when you are having a microservice or a pod in OKE. And then as your microservices keeps scaling, right, this is a very important topic because it becomes really difficult for a developer to start thinking about how would I control the communication between different services, right? How can I get an end-to-end visibility between my different services, right? That is when they have to start thinking something called as service mesh, right? So service mesh is something called as, it's a mesh layer. It's a mesh layer between the application and the Kubernetes cluster, right? So you don't have to really think about, do I need to really work with my network administrator to give me the access on, how to control the communications between my services, right? No, that's all gone. With service mesh, things would get easier, right? You don't have to. It's a scalable thing that you could use it for when your microservices are really growing there, when they're really scaling. And the way it works is, what we really do is, and like Jeevan also mentioned, right? What we do is we inject a proxy layer at your services. So any communication that happens really happens via that particular proxy in your data plane network, and we give you that API, we give you that CLI, we give you that console to really configure service mesh with few clicks. You don't have to really worry about installing proxies or writing code for different proxies, right? This is where things becomes easier using service mesh, and this proxy is something like it's really configured for you with few clicks. You don't have to really do anything. And then you get that end-to-end visibility. You get, your operational efforts are improved. You can be more productive, just focus on building on an application. You don't have to really write an application code to establish like an MTLS communication between microservices. You can get end-to-end visibility. You can do blue-green shift of traffic, all with OCI Service Mesh. And that's pretty much what I had. If you want to give me some feedback so that I can come up with some better content next time, this is my session. Go ahead and provide me feedback. And thank you, everybody, for having me here.